So I'm going to show a lot of things. A lot of them are low cost and easy to do at home. Some of them, if you're doing at home, you will need a parent to do them with you, and you will need to take some safety precautions. I've already sliced my hand open 5 minutes into my first show. So science can be dangerous, but it's fun and it's exciting. So hopefully you get some ideas for things here that you can go and try at home. The first experiment I'm going to show you is just involving a normal bike wheel, just taking off a road bike, but any bike wheel would be fine. Going to hook a bungee cord through part of it. And if I hold the bike wheel up and just drop it, what do you think will happen? If I just hold it up and drop it, I keep hold of the string, what do you think might happen when I do that? Yep, boy there. It'll stand up. Okay, any other thoughts? In the green jacket? Can mum shout it in a loud voice? Okay, it'll lie flat. And last thought? It'll lie flat. Okay, so hold it up. Yeah, and as we thought, it's going to lie flat. Nothing terribly exciting there. This time I'm going to give the wheel a spin, and then I'm going to drop it. What do you think will happen then when I hold it and give it a spin? What do you think? It's going to spin. I think that boy was going to say the same thing. Okay, so let's give it a good spin. So not only does the bike wheel stay upright, but it's also moving around in a circle. And it is eventually going to lie flat because it's going to run out of momentum, which is the energy that's keeping it going. And gravity is eventually going to win over. And it comes back round to lying flat. Why do we think the bike wheel stayed standing that time though, when it was spinning? Why did it stay standing and move around in a circle? What do you think? Because it has momentum? Yep. Because of gravity, was that? Yep. Okay. So a bike wheel is heaviest round this outside edge. And it's got a thing called conservation of energy. When I spin it round its axis, which is a bit running through the middle, the energy of the bike wheel is pushing round to its heaviest part, which is the outside. But because it's on the bungee cord, it's being held tightly in place. The bike wheel can't just roll off, but that energy has to go somewhere. And the energy from the spin is pushing round to the outside. And because of that constant push, that's what's keeping it up. The energy is forcing it to the outside, and it also spins round its axis because it can't just roll away. That energy is making it go round. It's very similar to figure skaters. When you watch figure skaters and they're doing their spins on the ice, when they have their legs or arms sticking out, they spin slower. When they tuck them in, they go faster. That's about the spread of the energy. And that's what's happening there with the bike wheel. The energy is spreading to the outside where it's heaviest, and it's making it spin around that axis. For this one, I have a normal potato. It's an unbaked potato. And I've stabbed it onto a big sharp knife, which I'm going to not cut myself on this time. What do you think will happen when I hit the top of the knife with the hammer? Any thoughts? Girl in the purple there? The potato's going to fall down, was that? Yep. Boy there, yep. It'll split. Sorry. Oh, break it. Break it or split, yep. Boy in the green. Big loud voice. Okay, we'll take one more. It'll fall off. Right. Let's give it a hit and see what happens. So what happened to the potato? It went up the knife. Or did the potato go up the knife? Who thinks the potato went up the knife? Who thinks the knife went down through the potato? Okay. Now they might sound like they're really the same thing. Well, if the knife goes down, surely the potato goes up. But in science, there is actually a difference between the two. The knife is lighter than the potato. So the potato has what's called inertia. It's on the end of the knife, but there was no force moving the potato. There was nothing pushing it. The hammer's hitting the knife, and that is forcing the knife down. Because the knife's lighter than the knife's easier to move than the potato as well. Part of this trick, though, is whenever I hit the knife with a hammer, my hand naturally is coming down, but you reset naturally your hand back up to where it was, and that's what fools the eye. So doing it slowly, you'll see there I'm lifting my hand. When it's done at speed, you don't notice that so much. So it's not that the potato was coming up the knife was being pushed down through the potato. That's a bit of physics. So was the bike wheel. Now we're going to have a look at a wee bit of chemistry. The first one is something that you could potentially do at home, but you will need a parent. The things are easy enough to get, it's just a wee bit tricky. In this bottle there's some warm water. There's a type of sugar called dextrose, which is a type of glucose. There's also a chemical in there called methylene blue, and methylene blue is used for cleaning fish tanks. So it's easy enough to get. And there's potassium hydroxide. Potassium hydroxide is a cleaning chemical. That's the most harmful thing that's in here for your skin. So when you prepare it, you need to be very careful and ideally wear gloves if you're doing that. I'm going to give this bottle a shake and we're going to see if anything happens to what's inside. Okay. We'll give that another shake. Okay. Now that is one of the signs that a chemical reaction is taking place. There's a few signs for different experiments, but one sign a chemical reaction is taking place is, did something change colour? And we saw that that did change colour. Because methylene blue, as its name suggests, is blue. When it's mixed in here though, it mixes with the potassium hydroxide. And the potassium hydroxide takes the oxygen out of the methylene blue. And that's why it loses its colour. But why do you think shaking the bottle gives the methylene blue its colour back? And I've told you what's in the bottle, apart from one thing. There's one thing that I never said was in the bottle. So if oxygen's being taken out when it's mixed, when it's in the liquid, but when I shake it, it's getting its oxygen back to change colour. What else must be in this bottle? Girl at the back with the stripy arms. No, I can't make out what's being said. What's up here in the bottle? I heard somebody shout it. There's air up there. And what's in air that we all need? Get on the unicorn jumper. Oxygen. So when the methylene blue is mixed in with the chemicals, the oxygen's taken away. But when I shake it, it's getting oxygen from the air in the bottle. It's going back into the methylene blue, giving it its colour back. And then when I stop shaking it, it goes back to this because the air comes back up to the top and the potassium hydroxide takes the oxygen back out of the methylene blue. Sticking with chemistry just now, I have my sidekick, who only has slightly less hair than me. And I have a bottle of acetone. Now, you might be familiar with acetone as the ingredient that is in nail polish remover. This experiment does not work with nail polish remover because it doesn't have a strong enough amount of acetone in it. So I'm using pure acetone. And the head is just made of polystyrene. Polystyrene is an absolute nightmare when it comes in your packaging to try and get rid of. Just takes up a lot of space. When you break it up, it crumbles everywhere. Acetone helps us out get rid of our polystyrene. Now, this is not a perfect way of getting rid of polystyrene. It makes it easier to get rid of. But if scientists in the future can keep exploring with different chemicals and different reactions, we might find a better way of getting rid of our polystyrene so it's not affecting the land and the wilderness. But for just now, we can see the effect of what acetone does to polystyrene. Okay. And just a very small amount of acetone melts the polystyrene head. It really doesn't take very much. And apologies to the people at the front who are getting this really strong smell of acetone. I will put the lid back on. Okay. Now, not only is it breaking it apart, you'll see that we're getting this sort of stringy goop coming from it, which is actually very sticky. It can be used like glue. But it also makes the acetone easier to dispose of because you can put it in a jar, seal the jar, and then bin that. That whole polystyrene head will gradually dissolve there in the acetone. It really won't take much more to get rid of all of it. Now, it looks like the polystyrene head is melting, but it's not actually that the polystyrene is melting. About 75% of polystyrene is just air. The acetone is breaking up the bonds that hold the polystyrene together, and the air is being released. So the polystyrene is being broken up in a chemical reaction, that air is released, so everything else just melts down, and you get that sort of goop. Again, simple one to do at home, but you do need pure acetone. Nail polish remover will not do the job. This next one, I have been told that you can get dry ice if you go to the supermarket and say to them, have you got any dry ice left over? Apparently they get it in their deliveries. That's not how I got mine. I ordered mine online. But if you're looking for something fun to do, especially at Halloween, you can see if your local supermarket has dry ice. And I'm going to show you a couple of cool things that you can do with dry ice, or a couple of cool things about dry ice. Now, dry ice can come in lots of different forms. You can get blocks, you can get pellets, which is what these are. And you'll notice, particularly the people near the front will be able to see, hopefully you can see at the back, that it looks like there's a sort of steam coming off the dry ice. Does anyone know what dry ice is made of? Boy in the green? Can somebody next to him shout it nice and loud? Snow? It does look a bit like snow. Normal ice is made of water, which freezes at 0 degrees. Dry ice is made of frozen carbon dioxide. Carbon dioxide is a gas, but it does freeze, but at very cold temperatures. Dry ice is minus 79 degrees Celsius. That's why I'm using tongs. If I was to touch the dry ice with my hand, I would give myself serious frost burns, could even give myself frostbite, which is why I'm touching it with the tongs. And we've got this sort of smoke coming off. That's because dry ice, unlike normal liquid ice, water ice, dry ice goes straight from being a solid to being a gas. And that's a process called sublimation. So as the dry ice warms up, it stops being solid and becomes a gas. The reason you can see the carbon dioxide in this sort of smoke is because it's mixing with water vapor in the air. Okay? So keep that in mind for the question I'm about to ask you. So dry ice goes from a solid to a gas when it warms up. In a jar here, I have some cold water, and I'm going to add some hot water to a separate jar. Okay. Now, people at the back will not be able to see this very well. I can try and lift them up once they're both going, but you're welcome to stand, you're welcome to move to the sides to be able to see. I know they set it up for sitting, but as long as everyone can see, I don't mind where people are. I'm going to put some dry ice into the cold jar and some dry ice into the hot jar. Put your hand up if you think the cold jar is going to produce the most smoke. Put your hand up if you think the hot jar is going to produce the most smoke. Put your hand up if you're somewhere completely in the middle. You've got no idea. Some, that's fine. It is okay to have no idea. I'll try and get the same amount into each jar to make it a fair test. There's the cold jar. Oops, dropped some. And there's the hot jar. Oh, I also should have said you're welcome to take any pictures and things. I've got a big social media presence, so I don't mind being in pictures, so you're welcome to. You'll notice that the hot jar is producing more of that smoke than the cold jar is, as most people predicted. And that's because it's going through that process faster. We've warmed it up faster by putting it in hot water, so it's turning to a gas quicker. What did you notice about the direction of the gas though when it came out? Where did it go? It fell down. And that's because the carbon dioxide, as it's becoming a gas, is heavier than the air round about. It's mixing with the water vapor, and it's pulling it down because it's heavier than the air round about. So you'll see dry ice being used in concerts, you'll see it being used in the theatre, film, television, to create a nice eerie atmosphere. And that's because it does fall down and float along the ground. So you get a nice sort of spooky fog in it. Have you got a question? It smells like smoke. It does have a bit of an interesting smell to it. I wouldn't recommend doing that too much though, because carbon dioxide is not something you want to be breathing in lots of. Who in here likes a gin and tonic? I'm not going to buy you one. I don't have any gin here either to give you one. But you can do something cool with your gin and tonic and dry ice as well. Because tonic water has an ingredient in it that makes it glow blue in ultraviolet light. Now, normally, a liquid just absorbs the ultraviolet and we absorb the ultraviolet. But there's a chemical in tonic water which reflects the ultraviolet light. And that's why we're getting this blue glow. Much more effective when it's nighttime or you're in a dark room, because it is a very vibrant blue glow and it does light up quite a lot Now, if you're doing this for Halloween or even just for fun, you can have your different potions here with your hot and cold water, but you can also have your glowing tonic potion. And adding gin to it won't stop the reaction from happening. So you can have your gin and tonic and have it glowing and smoking. Once all the carbon dioxide, once all the dry ice has become a gas and you've got no more lumps left in the liquid, you can actually drink the liquid. Some bars and restaurants do this when they bring you particular cocktails. They use dry ice. You just need to wait until there's no lumps in it. But it's then safe to drink because it's become a gas. The gas has come out the jar or out the glass and it's away. There's also some scorpions that use this with the ultraviolet light. They bury themselves in the sand during the day, but they can detect ultraviolet light and their bodies will glow. And people actually go out at night when the scorpions are active and they go looking for them using an ultraviolet torch because the scorpions will glow in the dark when the ultraviolet shines on them. Now, I doubt many of you have a glow-in-the-dark scorpion at home, but I'm sure tonic water is something that you'll easily be able to get, and you can have glowing potions, or adults, you can have a glowing adult beverage if you wish. I'm going to attempt something else for you with the dry ice. This is one of the trickiest things I have ever done. It was bad enough trying to film it at home without an audience. It's always a bit more tricky with an audience because you get nervous and is it going to work? I'm going to try and make a crystal ball for you using the dry ice. The submersible light I've got in this bowl is just to give it more of a crystal ball sort of look. I'm going to add in some hot water just so we can get as much smoke as possible from it. I keep calling it smoke. It's not actually smoke, obviously, but that's the easiest way to describe it. What's your question? You'll find out why there's a balloon there later on when I get that far. That's in dry ice. Now I've got a cloth here which has water and dish soap on it. And the aim is I'm going to drag it across the top of this bowl to try and create a film of dish soap, just like you would with like a bubble wand, and see if I can get a crystal ball for you. The hardest part about doing that is you cannot breathe while you're doing it because it will pop. I'll see if I can get it again. Sometimes it will last a while, sometimes it will just break like that. No, it doesn't seem to be catching again. Nah, it's not catching again. At least we got it working once, and I do need to move on. So that's another fun one that can be done at home, especially Halloween time. If you can get your hands on dry ice. It is quite expensive to buy from a supplier. So I wouldn't recommend rushing out to buy any. But if you can get some from the local supermarket, you can have a bit of fun at Halloween time. Okay. I've got a bit of string here which has just been soaking in this cup of water. And I've got a cup here with green water in it. Again, like the other experiments, that is just so you can see clearly what is happening. But what you are able to do, because water molecules all stick together, is you can get the water to run down the string into the other cup. Now there's a very fine balance between getting the water to run down the string and the water pouring out of the cup, which is why I've got this tray underneath. But you'll see the water's running down from one cup into the other. And that's just because water molecules stick together. They're like very good friends, water molecules. And because a bit of string was soaking in the water in the cup behind, when I'm trying to pour it out, the water from the cup with the green in it is sticking on to the water in the string. I was obviously doing that over a short distance there, but it can be done over greater distances. At my own school at Assembly, I did it from the top of a ladder, 18 feet across to the other side of the hall, down a bit of string. I just don't have the ability to do that here. Again though, dead simple to do at home. All you need is water, 2 glasses, and a bit of string. And that's it. But you're looking at very complex things in science when you do that. But really the simplest explanation is water molecules all cling together and they're sticking on that bit of string to run down it because they're holding on to each other. And I'm going to have a wee look at the properties of water like that in this next one, but there's also something else at work in this next experiment. I have a glass of water, just normal tap water, and I have a piece of card. I'm going to put the card over the top of the glass, flip the glass upside down and press it nice and tight onto the card. And now I have the water trapped inside the glass. Now that will not hold like that forever. I have done this lots of times before, and in a classroom once I stood for over 10 minutes with my hand like this above a sink while talking to the class about what was going on, and then eventually had to stop the process myself. I don't know how long this is going to last, but I don't want it to suddenly spill everywhere. I did make the mistake once though of at a school assembly doing that, and one of my party tricks with it when I've done it in class is I pass it over the top of my head. I did that at a school assembly, thinking it would be a good idea. And also thinking because the school assembly was going to the back of the hall, it would be a good idea if they could see the water clearly. So I had red food colouring in the water, got the glass to there, the card fell away, I had to go through from 9:30 in the morning to the end of the school day stained red because of that. However, children in the school still talk about it, and that was 2 years ago, and they still talk about that time Mr. Naismith got himself covered in red food colouring. 2.5 million people on TikTok have had a real good laugh at Mr. Naismith getting covered in red food colouring, particularly the comments like, at least his hair was fine. Which is fine, I'm a big boy, I can take it. But it brought a bit of excitement to science. I am not going to do that for you today, in case I need to go from now until the end of the day completely soaked. But try it at home. And it's up to you whether you pass it over your head. Children, do not do that without seeking your parents' permission first, because I don't want them emailing me saying, why did you do this? They're now covered in water and ruining their clothes. But it's good fun. You just need a bit of card, a glass, some water. Now, I'd said that I was looking at the properties of water there and the fact that water molecules stick together. But there's something else holding the card on there. The water's part of it, but what else do you think might be holding the card onto the bottom of the glass? And I'll give you a clue. It's something that's not in the glass. It's air. Well done. It is air. When that's flipped upside down, there's some air trapped inside the glass, and there's a pressure difference between the air that's trapped inside the glass and the air that's outside. The air outside the glass is trying to get in to balance that pressure, but the bit of card's there. So the air is pushing up on the card to hold it in. At the same time, the water molecules, which we saw with the string, all stick together. They're all sticking together on the surface of the card. So there's surface tension is what it's called when that happens, with the water sticking to the card, and there's air outside pushing the card up. And these two things work together. So air has pressure. But there's something else interesting about air when it's at different temperatures. For this one, again, simple one to do at home, just be careful where you do it. You need a tea bag, but you need the type of tea bag that comes folded up and stapled with a bit of string, because other types of tea bags don't work for this. I have tested, they don't do the job. You cut the top off them, you empty out all the tea, take off the string and the bit of card, open it up and close over one end. Now you're opening it up at the bottom so it can stand up. I'm going to set it on fire and we'll see what happens. Right. And it flies up. Now it does extinguish very quickly because there's not a lot of fire on it, but it floats up. That's another fun one for Halloween. It's actually great at any time of the year, but it's fun for Halloween because you can draw a ghost face on it and things and have a flying ghost. But that happens because warm air is lighter than cold air. That's how hot air balloons fly. They fill up the inside of the balloon with warm air, and because it's lighter, it moves up. And cold air also rushes in to fill the space where the warm air is going. So as the warm air starts rising up, cold air comes underneath, and that's what's lifting the tea bag. It's also what lifts hot air balloons, but they use a much bigger fire than I've got going there. Just making sure my kettle is boiling. While that's boiling, I've got a jar here, and I'm going to set a piece of paper on fire, put it inside the jar, and then I'm going to put that piece of that balloon on the top of the jar. What do you think might happen when I do that? It might disappear. What do you think? It might pop. It might. No? Okay, can you guys just take a wee step back? Just because I'm using fire, I don't want you too close, just to be nice and safe. So the fire goes out, and the balloon ends up getting pulled down inside the jar, and it's held quite tightly, and that's why I'm able to just lift this by holding the end of the balloon. Now think about what we've just said about air. What do you think is causing the balloon to end up in this jar? We've just talked about a couple of properties of air. So think about that. What's caused the balloon to get in? Well, air has done it, but what about air? What do you think is different between the air inside the jar when I've put the fire in and the air outside the jar. What do you think? Okay. Okay. What do you think? One side's pushing and one side's pulling. So warm air, as we said, it has less pressure and it rises. The warm air in the jar has risen up past the balloon. But I also said that when warm air rises, cold air needs to fill in where the warm air was. That cold air, as it's trying to come down to fill in, pushes the balloon down. It looks like it's a sucking action, but it's actually that the cold air outside pushes the balloon down. Getting it back out, you just need to give the balloon a wee squeeze to let the air out of the jar, and then you've got your balloon to use again. This is going to run just 5 minutes over the scheduled time, but hopefully you'll hang about for the big finish, and then it'll be a perfect time for lunchtime. For this one, I'm going to fill up this glass bottle with boiling water, put the stopper on and leave it for a minute. Then I'm going to pour the water back out, put in this stopper with a straw in it, and tip the bottle upside down into this bowl of red water. I'll take predictions while I'm filling this up of what you think you might see happen. What do you think will happen when I do that? Think the water will go all fizzy, boy in the green? Okay. Yep, what do you think? The water will turn red? Okay. Right, that's that filled up with boiling water. Somebody thinks the water will sit on top. Just put that on for a minute. That'll give me a chance to get my glove on. Again, if you're doing this at home, safety precautions. I was using my funnel to make sure I didn't spill boiling water on myself. I'm using a glove to make sure I don't burn my hand, because glass is an excellent conductor of heat. So this glass bottle is going to be really, really hot now. And I need to pick it back up to pour the water out. I'm going to pour it out, put this stopper and straw on the top, put it upside down, and we'll see what happens. And if people at the front are wanting to take pictures or film or whatever, remember, you're welcome to. So the water shot up the straw and into the bottle. And that's because this bottle had been warmed up, obviously, with the boiling water. And when I poured it out, that means all the air in that bottle is also warmer than the air outside. So the air in the bottle, because warm air has less pressure, it's not pushing on the water with as much force as the water outside. So the water out here is pushing down on there. And if the air pressure was the same in between them, the water would stay where it is. But because the air in here can't push back as much, the water gets forced the only place it can go, which is up through that straw, and that's why you get the fountain. Now you can do it without the straw. It just doesn't have the cool effect with the fountain. It's just that the water gradually comes up into the bottom. Okay. Now I recognise a couple of faces who were at the first show, who by the time we got to the big finish, our electricity had cut off and they missed it. So I'm glad to see a couple of faces back to see that. Okay. There was a man hundreds of years ago called Daniel Bernoulli who developed something called the Bernoulli principle. And it was a theory about the movement of air. And the Bernoulli principle said that fast moving air has less pressure than slow moving air. And we've seen that in a couple of these experiments. That's how houses get pulled off of roofs during tornadoes. It's not that the roof gets pulled off, but the fast moving air has less pressure, and the air likes to try and balance its pressure. So the air inside the house pushes up the way. So it's actually the roof gets pushed off the house rather than the tornado pulling it off the house. There's a simple experiment you can do to show the Bernoulli principle using a hairdryer, which is obviously not mine, and a balloon. Now, if I can catch the balloon in the airstream, I don't know if we've also got a fan in here which is affecting this. There we go, right, and I can take my balloon for a walk, if I can keep it in the airstream. Okay, and if I tilt it, oh, I think we do have a fan blowing up there as well. But you see I was able to take the balloon for a wee bit of a walk there. And that's because the fast moving air is holding the balloon in place. When I moved slowly, the balloon ends up staying in that stream of fast moving air because the air round about the outside of it has more pressure than the air in that stream that it's in. So it pushes on the sides of the balloon. This will probably work a wee bit better because it doesn't need to go as high, so it won't be as affected by any other airflows. But you can also do it with a ping pong ball. Right, and I can take my ping pong ball for a walk. And I can also tip to the side. Obviously, if you tip too far, it comes out of that stream, but you can tip it off to the side. And you can tip it off to the other side, and as you saw, you can take it for a walk. Now, if I move too quickly away from it, it will obviously drop, but as long as you move nice and slowly with it, and tip it nice and slowly and don't tip it too far, the slower moving air outside is going to hold it in that stream of air. That's how aeroplanes are able to fly, is because fast moving air has less pressure than the slow moving air. When an aeroplane's flying, it forces air quickly over the top of its wing, so the slower moving air underneath pushes up on the plane, and because the air above it's faster and isn't pushing down as much, the plane gets lifted by the air, and that's something called the Bernoulli principle. And you can see that with a paper wing. So if you imagine that's a plane wing, and I make a fast moving stream of air over the top, you'll see it lifts up. That's not the big finish though. We've got one more thing which uses the Bernoulli principle. If you create a stream of fast moving air over the top, things get lifted up into the air, as we saw with the paper and as we said with the planes. So with a leaf blower and a roll of toilet paper, and with cameras at the ready if you wish. In 3, 2, 1. Will we do one more? It's funny how quickly it goes back to COVID times with people fighting over toilet paper. So as we said, you'll have seen there, the toilet paper gets pushed up the way because of the fast air over the top. Okay. And 3, 2, 1.